In this lesson, we're going to talk about extrema and critical points. So first, we're going to focus on extrema. Extrema refer to maximums and minimums on a graph of your function. So there are two types of extrema that we have. We have absolute or global extrema, and then we have local or relative extrema. So they go by both names. I will refer to absolute extrema, and I will refer to local extrema, but just be aware of the different names for them. So absolute extrema is the largest or smallest function value over the entire domain of the function. So basically what that means is over your entire function, what is the largest or smallest overall? For the local extrema, that's the largest or smallest function value over a particular interval or in comparison to what's around it. So it might not be overall the largest or smallest, but in a particular area that you're looking at, when you check values to the left and to the right, it happens to be the largest or the smallest value. So when we're dealing with absolute maximum, this is just fancy math here. Basically, what it's saying is that if you have absolute maximum, then that value is the largest value on the entire domain of the function. If you have a local maximum, it is the largest value in a particular area containing that value. So if we're looking at a particular x value that happens to be a high point on your graph, we're checking the left and to the right of that value. And if it's the largest in that area, it is a local maximum. Same thing goes for a minimum. So the absolute minimum is going to be the smallest value on your graph overall. So over the entire domain of your function, what is the smallest point on your graph? For the local minimum, we're looking for the smallest value within a particular interval surrounding that value you're looking at. So you're constantly checking again to the left and to the right to see if you have the smallest value within a particular interval. Okay, a warning about endpoints. So I have this in red as a big warning. Endpoints can be absolute extrema, but are not considered local extrema, as we don't know what's happening to the graph after the point. Okay, and this will make more sense when we actually look at a graph. So here we have just some random graph, and we're going to identify the absolute and local maximums and minimums. Okay, so looking at this graph, we can see that my low points, right, there's like a lowish point over here. I'm going to do this in blue. There's a lowish point over here and a lowish point over here. Okay, looking at all of my possible low points, the lowest of all of those points is the one on the left. So this would be, I'm just going to put abs min. Okay, that would be an absolute minimum here because that is the lowest out of my entire graph. Now the other points that I labeled here, they're both low points in relation to where they are. So if I look at this point in the middle, to the left of it and to the right of it, everything is higher. So this would be a local min because it is the lowest point within this particular interval, like right around here. Same thing goes for this point over here, right? It is a low point, but it's not the lowest point on the graph. But in this vicinity over here, it is the lowest. So this would be a local minimum. Now when we go to look at the high points. So when we're looking at the graph, we can see that there's I'll do this in green actually. We'll do a high point here, here, and this is what I said to be careful about. So I'm going to not put a dot there, but I'll talk about that in a minute. So if I look at, even if you thought, okay, we'll pretend that that's a maximum, right? So we're going to look at all of the dots that I have up here. The highest one is this one right here, and we can see that. So this is going to be my absolute maximum. Absolute maximum. And when we have an absolute maximum or an absolute minimum, we could potentially also have a local. Now, in this vicinity, is this the highest? Yeah. Overall, is it the highest? Yeah. So it's an absolute maximum, but it's also, I'll put and, a local maximum because in this area, it is the highest. Over here, we don't have an absolute. It's not the highest, but we do have a local max. Now, the endpoints are tricky, and that was my warning on the previous slide. So I can see that this absolute minimum that I have here, this endpoint, is an absolute minimum, right? Is the lowest point on my graph. I don't know what's happening after this point. Like my graph kind of stops here, but does my graph continue to go down from here? Does my graph bounce back and come back up, right? I don't know what's happening to the left of this point. So I can't check for local extrema because I don't know what's happening after it. Whether or not it keeps going down or it changes direction and goes up, this is the lowest point on my graph. Could it go further down and have a lower point? Sure. But on what I see in front of me, this is the absolute minimum. So it's not a local minimum, but just an absolute. When I look at the other side here, at this end, it is not an absolute maximum because there's a higher point. And it's not a local maximum because, again, I don't know what's happening to my graph. Is my graph continuing to go up? In which case, this point is not a maximum. Is my graph going to, at that point, turn around and come back down? It could. At that point, is that a maximum? It could be, but we don't have enough information. So endpoints we don't call local. We can just define them as absolute max or min. So hopefully that makes some sense. There's a very important theorem. There's a bunch of theorems in calculus that are important, and this is one of the important theorems, is the extreme value theorem. So basically what this is saying is that a function that is continuous, and the key word here is it's continuous. So a function that is continuous, oops, as I draw across the thing, on a closed interval must have an absolute maximum and an absolute minimum on that interval. So looking at these three different scenarios, right, we can see that these are all continuous graphs. And at some point on this graph, we're going to have an absolute max and an absolute min. So here we can see that C is our absolute max, and we can see that D is our absolute min. Here we have C is our absolute max, and D is our absolute min, which also happens to be my endpoint. And then in this one, we have two absolute maximums because they're equal, C1 and C2. And then we have an absolute minimum here at D. Okay, so by a function being continuous, it guarantees that there must be an absolute maximum and an absolute minimum. Okay, so it could be an endpoint or it could be just some point on my graph. Here are some examples that do not fit the extreme value theorem. So the one on the left does not fit the extreme value theorem because it's not continuous, right? We have a not continuous. So since it's not continuous, it's not the extreme value theorem. Here, even though this is stopping here and continuing going up this way, and it's technically continuous-ish, because of this open circle, right? It's on an open interval. So on the extreme value theorem, it has to be on a closed interval. So open interval. So this makes the extreme value theorem not true, or it doesn't fit it here because it's not a closed interval. Even though it seems to be continuous, it's not continuous at this point because it's open. So how can we go about finding the extrema of a function without looking at the graph? So if we have a graph, right, it's pretty easy. Look at the graph, look for the highest and lowest points, and there you go. But if we only have the function itself and we are not able to graph it, we can use derivatives. So there is a type of point called a critical point, and these are points on a function graph at which the derivative is either 0 or undefined. Okay, so basically there's a critical point, and we'll call it C, which is some number, in the domain of the function f, such that f prime of c is equal to 0, or f prime of c does not exist. Okay, the extrema, both local and absolute, can occur at these points. So they are critical. So let's look at an example. So find the critical points of f of x equals x to the 3/5 times 4 minus x. So we have to find the derivative of this. So we can do one of two things. You can either use the product rule, or you can distribute the x to the 3/5 and use the power rule, which I'm going to do because it's a little bit easier. So I'm going to rewrite this as f of x equals, this is going to be 4x to the 3/5 minus x. So now when I multiply x to the 3/5 times this negative x, this is really x to the 5/5. When I multiply, I'm adding my exponents together, so I'm going to get 8/5. So now I can take the derivative of this by using the power rule. So f prime of x is equal to, we're going to multiply 3/5 times 4. So we get 12/5 x to the 3/5 minus 1, so minus 5/5. We get negative 2/5. And then minus 8/5 x to the, again, subtract 1, so we're subtracting 5/5, so we get 3/5. So from here, I'm just going to clean this up a little bit myself. So I'm going to make this 12 over 5x to the 2/5 minus 8x to the 3/5 over 5. So I'm going to get a common denominator here just to make this a little bit nicer. So I'm going to multiply by x to the 2/5 on the top and the bottom. So now I have f prime of x equals, they're going to have a common denominator of 5x to the 2/5, so I can combine the tops together. So we get 12 minus x to the 3/5 times x to the 2/5 is x to the 5/5, which is just x. So this is going to be minus 8x over 5x to the 2/5. So here's my derivative. So now what I'm going to do is to find the critical points, that's going to be where the derivative is equal to 0 and where it does not exist. So I'll put this over here. So f prime of x is equal to 0 when the numerator is going to equal 0. So this happens when 12 minus 8x equals 0. So now if I just solve for this, 8x is equal to 12, so x is equal to 3 halves. And that's one critical point. And then I also have to see when f prime of x does not exist. So f prime of x doesn't exist, in this case, wherever the denominator equals 0 of this fraction. So when 5x to the 2/5 is equal to 0, so that would be when x is equal to 0. Okay, so I have two critical points, 3 halves and 0. Okay, let's look at another example here. Find the critical points of this. So again, find your derivative. So f prime of x is equal to, this would be 3x squared minus 18x plus 24. Since this is a polynomial, there is no point where the derivative would not exist. So we only have to check where this is equal to 0. So 3x squared minus 18x plus 24 equals 0. Okay, so sometimes there'll be points where the derivative doesn't exist, but if there's not one, don't worry about it. So I'm just going to factor this. I'm going to divide everything by 3. So x squared minus 6x plus 8 equals 0. And then I'm going to factor. So x minus 4 and x minus 2 equals 0. So I end up with my critical points, x equals 4 and x equals 2. Okay, so this one's a little bit different because we have absolute value going on here. So find the critical points of this. So first thing I'm going to do is I'm going to factor what I have inside. So I'm going to rewrite this as y equals the absolute value of, if I factor this, I'm going to have x minus 3 and x minus 2. So I'm going to graph this so we can kind of see what this is all about. So if I set it to 0, I have x-intercepts at 2 and at 3. So 2 and 3. Actually, let me just space this out better so it doesn't look so crazy. I'm just going to call this 2 here, and I'm going to call this 3 here so we can just see it. So when I'm graphing absolute value of a parabola, since it's absolute value, it has to be positive. So normally my parabola would look like, oh, this is really bad, something like this, right? Because it's going to be opening up because the a value is positive, and it's going to cross at 2 and 3. But because it is absolute value, we can't have this negative piece down here. So we have the piece, up here and up here, but then this piece has to like reflect up. So it's going to become that. So I'm going to get rid of the bottom piece so we don't get confused. Okay, so my absolute value is just all positive, right? So we're going to kind of reflect that piece up. So looking at this, right, we want to find where the derivative is equal to 0 and where the derivative does not exist. So looking at this, I can see that I have a slope of 0. Oops, right there. So I still have to take the derivative of this entire thing, right? So if I take the derivative, that piece is part of like the negative version of this graph. So when I'm graphing absolute value, remember what's inside can be positive or negative. So the positive version of this looks like this, right? The negative version of this is going to look like this. Oops. So because it's absolute value, we're getting rid of anything that's negative. So like, oops, right? So that's how we get the graph that we see here. So the piece that has the derivative of 0 is actually the piece that's the negative version of the quadratic, so the part that's going like that. So when I take the derivative, I'm going to use y as the negative version, so negative x squared minus 5x plus 6. So I'm going to do y equals, I'll just distribute that, so negative x squared plus 5x minus 6. So what I'm going to do here is just take the derivative of this. So I have negative 2x plus 5, and then I'm going to set that equal to 0. So I get negative 2x equals negative 5. So x is equal to 5 over 2. So this is one of my critical points because that is where my derivative is equal to 0. Now notice at 2 and at 3, we have those points where it's not differentiable, right? Because remember we talked about differentiability and we said when we have like a v, that's not differentiable. So what's really happening, my bad drawing I guess is hard to see, but we really have like a v at 2 and a v at 3. So we can say that y prime does not exist at x equals 2 and 3, and that's because it's not differentiable. Okay, so wherever we have those pointy pieces, it's not differentiable, so that's where this does not exist. And then, or where the derivative does not exist. And the derivative is equal to 0, where we have a horizontal tangent line, and we can see that that's on the negative version of this function. So every local max or min is a critical point, but be careful because the converse of this is not true. So every critical point is not necessarily a max or min. So when we have a max or min, a local max or min, it is a critical point. But if I have a critical point, which is where the derivative is 0 or doesn't exist, so in this case, we have a derivative of 0 right here, but that is not a max or min because my graph is constantly increasing, so there's no change from increasing to decreasing, so there's no max or min here. So just be careful with that fact. So now we're going to look at how we actually find absolute extrema when we're looking at a function. Okay, so to find an absolute max or min of a continuous function on a closed interval a to b, we note that either it is a local max or min or it occurs at an endpoint of the interval. Okay, so here are the steps that we're going to use. The first step we're going to do is we're going to find the function values of the critical points within the open interval. So just find the critical points like we did in the last examples. Step 2, find the function values of the endpoints of the interval. So we have to check our endpoints. So endpoints, remember, can be absolute extrema, but they cannot be local extrema. So the critical points are kind of helping us with the local extrema part, and then the endpoints are helping us with the absolute because, well, they're all going to be absolute, and we're comparing all of them to see if it's absolute, but we can't consider the endpoints local, but we have to use them separately because they're not part of the critical points necessarily. So then part 3, or step 3, is the largest of the values from steps 1 and 2 is your absolute max value, and then the smallest of these values is the absolute minimum value. Okay, so hopefully this will make a lot more sense when we do an example. So find the absolute maximum and minimum values of the function this on the interval that. Okay. So first thing I'm going to do, go back to here real quick. First thing I do is find my critical points. So here I have a f prime of x. Take the derivative of this. So I'm going to have 3x squared minus 6x. Because it's a polynomial and I don't have like a fraction or any denominator that could potentially be 0, there's going to be no point where the derivative does not exist. So all I have to do is set the derivative equal to 0. I can factor out a common factor of 3x, so I have x minus 2. When I solve, I get x equals 0 and x equals 2. So those are my 2 critical points. So what I'm going to do now is I'm going to make a little chart. So I'm going to make an x. Oops. Whoa, that's a bad one. Hold on. Redo. So I'm going to make a chart of x and f of x, and I'm going to use my endpoints as well as my critical points. So I like to kind of label these. You don't really have to, but I like to put EP for endpoint. So my endpoint, farthest left endpoint, is going to be -0.5 because that's my interval. And then my furthest right endpoint is 4 because that's farthest to the right. And then I have these 2 critical points and they're in the middle. So I just put them in numerical order. So I'm going to have 0, which is, I'm going to put CP for critical point, and 2, which is a CP for critical point. Okay, so I have my endpoints and my critical points. So all I'm going to do now is I'm going to check the value of my function at these points. And notice that I'm using f of x, not f prime. So we're using the original function here, and we're plugging in the points. So if I plug in -0.5 in for my x's, I'm going to get 1/8 for my f of x. If I plug in 0, I'm going to get 1. If I plug in 2, I'm going to get -3. And if I plug in 4, I'm going to get 17. So looking at my f of x values here, the largest one will be my absolute maximum, and the smallest one will be my absolute minimum. So I'm just going to write it absolute maximum. That's going to be 17. And my absolute minimum is going to be my lowest value, which is -3. Okay, so we're finding our critical points. We're making a chart with the endpoints and the critical points, plugging them into the function and seeing which of the y values is giving us the largest or smallest value. Okay, let's look at another one. So same thing, find the absolute max and min. So what I'm going to do first is find my critical points. So I'm going to take the derivative, f prime of x. This is going to be 1 minus 2 cosine of x. So there is no point, again, where the derivative would not exist. So I'm going to set this just equal to 0. So I end up getting 2 cosine x is equal to 1. So cosine x is equal to 1/2. So I have to figure out the cosine of what is 1/2. And the interval is from 0 to 2 pi. So that's going to be at pi over 3 and 5 pi over 3. So these are my 2 critical points. So now I'm going to make an x, oh my gosh, just bear with me with that, f of x chart. So I'm going to use my 2 endpoints. So I have 0. And so you can put the EP or not. I usually like to, but I guess I won't do it right now. So 0 and 2 pi are my endpoints. And then I have pi over 3. And then I have 5 pi over 3 as my critical points. So these I'm going to plug right into my original function. So I'm going to plug in 0, and I get 0. I'm going to plug in pi over 3, and I get about, I'm just going to put about negative 0.685. So remember, if you're using decimals, 3 decimal places or more. For 5 pi over 3, I'm going to plug that in, and that's going to be about 6.968. And then when I plug in 2 pi, that's going to be about 6.28. So we can use exact values or approximate values or whatever. So here again, absolute maximum is going to be the largest value that I got for my y values, which in this case is 6.968. And then my absolute minimum is going to be the lowest value I have, which is negative 0.685. Okay. So here we have another one. Again, same idea. So we're going to take the derivative, so f prime of x, and we have, I'm just going to write this out as the simplified version. So it's going to be negative 2 over 3 cubed root of x minus 1. So if you take the derivative of that, you have like negative exponent. So I'm just kind of jumping to simplifying. So when I look at this, right, since I have a fraction, in order for my derivative to be 0, the top would have to be 0, but the top does not have a variable in it, so I can't solve it to be 0. So there's no point where the derivative is equal to 0. But again, because I have a fraction, when the denominator is 0, that's where my derivative would not exist. So f prime of x is going to be dne, does not exist, where the denominator is 0. So that's going to be, I'll just put at x equals 1. So if I plugged in 1 here, 1 minus 1 is 0, cubed root of 0 is 0, times 3 is 0. So the only way to get a 0 on the bottom is if x was 1. So that's going to be my only critical point here. So again, I'm going to make an f of x chart. I'm going to plug in my endpoints, so negative 1 and 2, and then I have my critical point of 1. So if I plug in negative 1, I get negative 0.587. If I plug in 1, I get 1. If I plug in 2, I get 0. So we have an absolute max at 1, and we have an absolute min at negative 0.587. Okay, and then the last one we're going to look at here. So again, same thing. So find the critical points first. So f prime of x is going to be, here we have 2x minus 8 times the derivative of ln x. So the derivative of ln x is just 1 over x. So it's going to be 8 over x. So what I'm going to do here is get a common denominator, right? So right now it's really over 1. So I'm just going to multiply by x here and here. So I'm going to get f prime of x equals 2x squared minus 8 over x. So we have a fraction, so that means that we have to set the top to 0 for where the derivative is 0, and set the bottom to 0 for where the derivative does not exist. So I'm going to say f prime of x equals 0, and that's going to be where 2x squared minus 8 is equal to 0. So 2x squared is equal to 8. X squared is equal to 4. So x is equal to plus or minus 2. And then f prime of x does not exist when the denominator is 0, so when x is equal to 0. So I have 3 critical points here. I have 2, I have negative 2, and I have 0. But what we have to do is look at the interval that we're given. So it wants us to look at the interval from 1 to 4. So 0 is not in the interval. Negative 2 is not in the interval. So when I'm making my f of x chart here, that's why I always start with the endpoints. So I put the endpoint here of 1 and the endpoint here of 4. So now when I go to fill in my critical points, if the critical points are outside of these endpoints, I can't use them. So negative 2 doesn't work. 0 does not work. The only one that does work is positive 2. If I plug in 1 into my function, I'm going to get 1. If I plug in 2, I'm going to get 4 minus 8 ln 2. And if I plug in 4, I'm going to get 16 minus 8 ln 4. So I'm just kind of keeping it sort of exact. If I plug it in the calculator, this one gives me negative 1.545, and this one gives me 4.910. So my absolute maximum would be this 16 minus 8 ln of 4, and my absolute minimum would be this 4 minus 8 ln of 2.